start it. All right, so last time we went ahead and did this example, parts A and B. We're not going to be worried about part C, just because there are some other things that that we're not really going to get involved with. We could do part C. It's that initially it looks a bit weird for us to actually go through it. All right, so we had this example 3. Now I wanted to go ahead and look at example 4. Why is that still showing up here in the corner? Determine the horizontal asymptote for the following functions if there is any. So based off the previous notes that we've done already, does anyone remember, first off, what is a horizontal asymptote, more or less? Just give me an idea of what it might be whenever I talk about a horizontal asymptote. Well, we'll get rid of the obvious stuff. It's a horizontal line. It's a horizontal asymptote, so it is a horizontal line. But what's so special about this line in respect to a function? Yeah, exactly. It's an imaginary line, if you want to word it that way, where if I draw my graph, it gets really close to that line, but they never actually touch or cross each other. So a horizontal asymptote is a horizontal line that my graph gets really close to, but never actually touches or crosses. All right, so that was what we define as a horizontal asymptote, more or less. We also remember that to get a horizontal asymptote has the form y is equal to the limit as x goes to infinity of the function, whatever that value might be. So if the limit was 4, then my horizontal asymptote would be y is equal to 4, for example. It would be whatever this value is, y is equal to that. So if I'm looking at part A, for example, I want to find the horizontal asymptote of this given function. F of x is equal to 5 times the square root of x plus x to the negative 6 power over 3x minus 8. All right, so looking at what I have here, again, if I want the horizontal asymptote, I need to find this limit as we go off to infinity. So for part A, my answer will be y is equal to the limit as x goes to infinity of this function. 5 square roots of x plus x to the negative 6 power all over 3x minus 8. So we have that so far. Now, pretty much our job is, what is that limit, whatever it might be? So we're going to do a little bit of our tricks here. First off, remember whenever I'm dealing with a polynomial, or not just a polynomial, but in general, really we're looking at the dominating behavior of the top and the bottom. So if I look at the top of this function, 5 square roots of x plus x to the negative 6 power, there's 2 parts to this, the 5 square root of x and then the x to the negative 6 part. Which one dominates the behavior of the top, the x to the negative 6 or the square root of x? X to the negative 6? Do we have agreements or disagree? Or there's also third option, no idea. So think about what happens if we go off and plug in a huge number. Which one of these is going to contribute more? If I did 10 million, would it be 5 square root of 10 million contributes more, or 10 million to the negative 6 power? Yeah, this part's going to end up contributing more because it's going to be 5 times a huge number. This number, if I plug it in, 10 million to the negative 6, that's 1 divided by 10 million to the 6. This is a really tiny number, actually. So really on top, that dominates my behavior. What about on the bottom and the denominator? what is dominating the overall behavior? Do you think it would be 3x or a -8? 3x. Again, you can imagine if I plugged in 10 billion, which one's going to contribute more to the overall value? Well, 3 times 10 billion, that's a huge number, versus -8. Clearly, 3x will be larger in the long run. So I'm using this idea where I'm looking at the dominating behavior on the top and the bottom. So really, I'm not worried about what's going on over here. I only care about the overall dominating behavior. What's going to happen in the long run. All right, so looking at this, I have 5 square root of x over 3x. So one way that I can go ahead and actually write this is now equal to the limit as x goes to infinity of, on top we had 5. And for convenience, I'm going to write it as a power. Remember, square root of x, that's the same thing as a 1/2 power. And then 3x. So these limits are the same. I'm not saying that this whole expression is the same thing as what we have here, but the limits are equal to each other. Again, because we only care about the overall dominating behavior. All right, so what's really good about what I wrote here, 5x to the 1/2 over 3x? Well, I can clean that up a little bit. There's an x on the top, x on the bottom. I should be able to do some cleanup work. So I can write this as the limit as x goes off to infinity of, well, 5/3. That still stays the same. How do I cancel out x to the 1/2 on top versus x on the bottom? So as a reminder, if I wrote this, x cubed over x, what would you say what that is equal to? Yeah, so if I look at this, you would say that this is a x squared, for example, because this is x times x times x divided by x. And then you'd be left with x squared. Or you can say x to the 3 minus 1 power. So if I look at this right here, I get x to the 1/2 over x. Using this idea, what does that simplify into? 1/2 over x. Let's see if I take this. Let's see if I have any other. Whenever I take x to the 1/2 divided by x, that should be the same thing as x to the 1/2 minus 1. Just like right here, this was 3 minus 1. I got 2. So here, when I do x to the 1/2 minus 1, I should get, let's write it over here, x to the -1/2 power, for example. So remember, this is how we simplify our exponents. Just like what we have here, it's the same idea, just instead of a whole number, it's with a 1/2. I claim that you know how to evaluate that last limit. What is that last limit going to be equal to? What happens if I plug, quote unquote, plug in infinity into that expression? Let's start off with this. What happens whenever we have a negative exponent? Yeah, it goes on the bottom, right? So if you want, you could take it one step further. I'm running out of room here, but you can write this as 5 over 3x to the positive 1/2. Because negative exponent means that we can pop it to the bottom, or vice versa. All right, so why is it great that there's an x now on the bottom like that? What happens if I plug a huge number into that expression? It would just be really tiny, right? Because you get 5 divided by some huge number, 3 billion, for example. So based off of that, y'all told me it becomes a small number. But what number in particular? 0. It's an ugly 0, but 0. So this limit is actually 0. So I did this in a little bit of a long fashion. I actually could have looked at this from the very beginning and said, I know that this is 0 without having to really go through each and every one of these steps. First off, dominating behavior. We agreed on this, right? 5 square root of x, 5x. Which one has a higher power? Square root of x or a plain x? Square root of x. Because remember, a square root of x, that's the same thing as x to the 1/2. So which one is, quote unquote, larger? X to the 1/2 or x? So if I'm comparing the two, not half as much, but it's a square root of it. So if I compare these two, x is contributing a lot more compared to the square root of x. You can do, again, plug in 10 billion. Would you rather have the square root of 10 billion or just 10 billion? 10 billion would be more dominating overall, dominating the behavior of this function. So since the bottom had a larger dominating behavior, that means we're going off to 0, because we always know the bottom is going to be larger and larger compared to the top, which leads us to 0. So actually, whenever we get to exams, if you want, you could show all of this work, or you could just very quickly say, all right, the bottom power is larger for x. It should go to 0. And that's actually going to happen a whole lot for us. And I'm using this to help build our theory for the next couple of slides. But our final answer for part A is 0. Any questions about that part A? Let's go ahead and look at part B now. Same instructions. F of x is equal to x to the 4th minus 196 over x squared minus 14. I'm going to do this the quick way. It is going to be infinity. Let's talk about how we get that. On the top, what's the highest power for x we see? Yeah, we have 4, or I'm just going to circle this. This is my dominating behavior on top. What about on the bottom? Which one has a higher power, the top or the bottom? The top. So that means the top will always be larger than the bottom as we go off to infinity. Or you can write it like this. The limit as x goes to infinity for this function, really we care about this, the dominating behavior in the long run. What does x to the 4th over x squared simplify into? Yeah, so x to the 4th over x squared, that's going to become an x squared. And then we can go back to our informal idea. What happens if you plug infinity into there? You get infinity squared, which is still infinity. So the limit is infinity. What does that mean for our horizontal asymptote? We know my horizontal asymptote is usually y is equal to whatever number. Because here we had 0, so our answer was y is equal to 0 for the horizontal asymptote. Yeah, it's actually going to turn out that we do not have one. The reason being is this doesn't really mean anything for us, because infinity is not actually a number. It's an expression that means I keep on getting larger and larger. So this means nothing for us. So that means there is no horizontal asymptote. So if you get a plain number, a finite number, your answer for the horizontal asymptote will be y is equal to whatever number, like how before we had y is equal to 0. But if you get an answer like infinity or negative infinity or does not exist, then we actually have no horizontal asymptote. Mainly, largely because infinity is not actually a number. It's an idea that we're just getting larger and larger. Any questions about what I just done here for part B? As sort of a side topic, can someone tell me why do I not want to consider infinity to be a number? Why is it not definable? So here's an idea about it. If I did say that infinity is a number, that implies that there is a number bigger than that. But then that doesn't make sense because infinity is supposed to be my quote unquote largest number. So if I do call it a number, that means there should be a number bigger than that. I should be able to say what's infinity plus one. That should be another larger number. So that's just getting a little bit technical and like being very strict about the wording. But again, infinity is not really a number. It's just an expression or a concept. All right, so this was example 4. Let's go ahead and clear this one up. All right, so what we've just done here, this next slide, I don't want you to write down the slide. I just want you to listen and look at it. So let's say I have a rational function. So something that has like a fraction, it looks like a fraction. So it looks like I have some expression on the top, some expression on the bottom, where the top is a polynomial and the bottom is a polynomial. Remember, polynomial, this just means I have a long line of x's to a positive whole number power. This is just the very general form. Well, if I want to take the limit of this rational function, as it turns out, I just have to look at the power on the top and the bottom, that largest power on the top and the bottom. If the power on the top, put here, and we'll write this as, if the power on top is smaller than the bottom, my limit is always 0. And we saw that earlier. This one, the power on the bottom is larger. So my limit was 0. If the powers are equal, we're going to do this thing called a ratio of the coefficients. I'll do an example with that in just a moment. And then if the power on top is bigger, then my answer is going to be infinity or negative infinity. And we saw that again with that previous example. Right here, the power on top was larger. So I knew that my answer was going to be infinity or negative infinity. It depended on what I was working with. So we're actually going to use these 3 theorems to do all of these limits really fast. We're not going to worry about the proof. This is more like whenever I wanted my students to do a very intense proof version of it. If you're interested, you can always look at this in the notes. Let's go ahead and jump into this example here. I'm going to claim that y'all can do these each one within 10 seconds after knowing these rules, without having to do any of those calculations that we did earlier. Evaluate the following limits if possible. So the first one, I've got the limit as x goes off to infinity of 6x over 36x plus 1. The main question I'm going to ask each time I'm dealing with these is, what's the highest power on the top and the highest power on the bottom, and its coefficient? So looking at part A, what is the highest power term that I see? Yeah, so if I look on the top, the highest power is 6x, because x to the 1 power, and there's nothing else. What about on the bottom? All right, are these powers for x the same or different? Is their exponent the same? Yeah, so what that previous slide was saying is if the powers are the same, then all I need to do is look at the coefficients. That is the number in front. The number in front of this first one. What's the number in front of the bottom one? What does this clean up into? We're done. So if the powers are the same, I take the coefficients and make it into a ratio. The coefficients being the numbers in front of that x. Yes. Oop, yeah, so this is the limit. So notice I did very little calculations. The most calculation you did was what 6 divided by 36. Now I'm going to try this with part B. What's the highest power on top for part B? What about on the bottom? Yes, this is where I want you to be careful. We don't always have the highest power in the front. That's ideal, but make sure you actually read the entire bottom portion. Make sure you don't just say, well, x to the 4th on the bottom. It's actually x to the 6th power. All right, so is the power larger on the top or the bottom? All right, so that theorem that I showed you tells me if the power on the bottom is larger, my limit as x goes to wherever infinity is 0. Again, 0 calculations. Again, 0 is our answer. So examples part A and B, these are probably the most ideal situation because one is you take the ratio. The other one, you get 0 no matter what. Part C is probably the only scenario where I do have to put a little bit more work and context into it. So for part C, what is the highest power term on the top? Yeah, this whole 42x to the 8th. And what about on the bottom? Yeah, 18x to the 6th. So now we have the quick question is the power larger on the top or the bottom? The top. So whenever the power on top is larger, then my answer is only one of two possibilities, either infinity or negative infinity. So just for notes, I know that this is either infinity or negative infinity. We don't know which one yet. But even if I get to this point, and if I sort of guessed and I sort of have a 50-50 chance, more or less, that's much better than where we started off with. So now the question is, how do I even figure out what's going to happen here for if it's infinity or negative infinity? So we can actually do this as a little bit of a limit analysis practice. So first off, I'm taking the limit as x goes to negative infinity. So in other words, I'm plugging in large negative numbers into here. So if I'm looking at this first part, what happens if I plug a negative into the top portion that I've circled here? Is it going to be positive or negative? Let's see. If I take a negative to the 8th power, is that positive or negative? Yeah, because a negative number to an even power is positive. So positive number times a positive 42, is that positive or negative? Yeah, so on the top, it's going to be positive no matter what. What about the bottom? Is that going to be positive or negative? Yeah, it's going to be positive for pretty much the exact same reason. If I plug in a negative into here, a negative to an even power is positive. A positive times 18, that's still positive. Notice that I did not use this at all. I don't care about these lower ordered terms. I only care about the dominating terms here. All right, so what happens whenever I do a positive divided by a positive? So based off what I just said, what do you think the final answer is going to be, positive or negative infinity? Yes. So what I just did was sort of, informally speaking, called a limit analysis. Without really having to plug in a bunch of numbers, we know that my answer was infinity or negative infinity. I just needed to know, did I end up with a positive or a negative in the long run? So those are my three scenarios that we actually talk about for evaluating limits at infinity. So to do some recap here also, is whenever the top equals bottom power. Right here we have the top power is smaller than the bottom power. And then this last one was whenever the top power was greater. All right, so those are the three scenarios that we encounter for a limit. With part C being probably our most complicated scenario. Any specific questions about this? Do you have a question about what's going on here?
How do you know that it's going to be infinity?
Yeah, so at this bottom, for this bottom one. All right, so I'm going to start off with which one has the higher power, the top or the bottom? So whenever I know that, I know I only have two options, infinity or negative infinity. And then from there, we did the positive and negative to see which one was it. So if you ever get top power is larger, you only have two options really. If you want it, you could try to test this out. If you plug in, again, 10 billion into that function, you're gonna end up with a positive huge number. You're not gonna approach a single value. All right, so we've just gone ahead and evaluated our limits at infinity. And I think that this is actually a good stopping point because I believe next time we will be covering, let me take a look just to confirm what we cover next time. Great, so next time we are going to finally introduce one of the big pieces of Calculus 1. What is the derivative? It's going to be a very algebra heavy section tomorrow. All right, but besides that, I'll see y'all on, wait, today's Thursday, right? I'll see y'all on Monday. Oh, yeah, it's Labor Day, Tuesday. All the days are running together.